Hey, this is a continuation from the types of reactions, and now we're going to do a little bit more of that predicting products. So we're going to start with synthesis. In synthesis, you kind of the giveaway is that you're only going to have one product. An example that I have here, aluminum metal plus oxygen gas, remembering oxygen is diatomic, will form, and then when I get to this point I do need to think about their charges and make sure that I balance charge and that they're neutral. So it would be Al2O3. And then after that I can definitely balance it by trying to get 6 oxygens, and then I would need to have 4 aluminums. Second type of reaction we've talked about is decomposition, and this is the opposite of synthesis, where you have one reactant that breaks up into pieces or product. So example, water will decompose into, again, I'm just breaking it into its 2 elements. You just have to remember hydrogen and oxygen are diatomic, and then you can balance, and that is kind of, just one example of what a decomposition reaction might look like. Here's some other more complicated decompositions. The one that I just did is just a binary compound with 2 elements. It's just going to break into those 2 elements. But when you have more than 2 elements, there's a lot of these, but we're only going to focus on 2 of them. So a metal carbonate would be just some metal X with that polyatomic ion carbonate. It's going to break down into a metal oxide and carbon dioxide. So, and you have to be able to figure out kind of what your possible subscripts are. So, for example, lithium carbonate. Lithium is +1, carbonate's -2. So I know that I'm going to get the metal, which is lithium, is going to go with oxygen. So I'm thinking, okay, lithium's plus, it's going to go with oxygen. So then my formula would be Li2O. And then I'm also going to get carbon dioxide. So metal carbonates are always going to give you that metal oxide. Oops, not that one. And then they always give CO2. So the metal will go with the oxygen, and you always have to, crisscross or think about balancing charge. One other decomposition reaction that's a little bit, again, more complicated because there's more than just 2 elements is metal chlorates. So a metal chlorate would be, sorry, one second, I gotta pause this. So a metal chlorate, so chlorate's the polyatomic ion ClO, is going to break up into a metal chloride, and again you have to look at charges to figure out the formula of that, and you're always going to get oxygen. So for example, if I have potassium chlorate, it will break into potassium chloride. I know the formula because I know this is +1 and -1, by the way. So if it wasn't, I would have to do that balancing of charge and then plus O2. The previous one was balanced. This one needs to be balanced. So I'm going to go try to get 6 oxygens. And then I would need to get 2 potassiums and 2 chlorines. Next type of reaction is single replacement. This is when a metal alone can go in and kick out the other metal in a compound, so that you end up with a new metal by itself and a new compound. When you do single replacement, you're going to use the activity series to figure out which metals can replace which. So for example, lithium is the most reactive, so it'll be able to replace any other metal that's underneath it. Sodium is very reactive, but not reactive enough to replace lithium. So when I do a problem, which we'll do in the future slides, I can figure out whether it's going to happen, and then I can predict the products. So it's also possible for a nonmetal. If this is a nonmetal, it's going to replace the nonmetal, which is this part of the compound. In this, we're going to focus on just the halogens, group 17. And again, this activity series tells you, like, fluorine can replace chlorine, bromine, or iodine. Chlorine cannot replace fluorine, but it could replace bromine or iodine. And poor little iodine cannot replace anything. It's the most unreactive. So, let's do a couple examples. So this first one, lithium, is going to react with magnesium chloride. So what I want to do is I have to find these two metals in the activity series. So the single metal has to be higher than the one it's going to replace. It is. So this reaction will happen. If it wasn't, then you would just write no reaction. So the lithium is going to go in and push out the magnesium, essentially, and then the lithium is going to go with the chloride. So notice the formula here. Lithium is plus, chloride's minus. Some of you I know might be tempted to put a 2 because you know that chlorine is diatomic, but it's only diatomic when it's by itself, not in a compound. But I would balance this one with a 2 and a 2. So single replacement, like I was showing you earlier, you know, this is fluorine and then sodium chloride. So because this is a nonmetal, the fluorine has to be higher than the chlorine that it's going to replace, and it is. So this will happen. So you would form sodium fluoride plus chlorine. And then you'd want to balance. If we have iodine plus sodium bromide, again, the iodine has to be more reactive than the bromine. And I go over here and I know that it's not. It's too low. It can't replace it. So that would be an example where you would just say, no, this isn't going to happen. No reaction. Double replacement reactions, these happen. There's 3 reasons why they do. 1 is the formation of a precipitate. 2 is the formation of a gas. Or 3, sometimes they form water. So when you do a double replacement reaction, I like to think of these metals. You know, the metal would come first. So it'd be like the A and the B are going to switch spots. So what we're going to do, we'll do this one example. So silver nitrate and potassium chromate. So when I try to predict my products, I know the silver and the potassium are going to switch spots. So silver is going to go with the chromate. How do I know to write that formula? I know that silver is plus, chromate is minus 2. And I'm going to get potassium nitrate. How do I know this formula? I know K is plus, nitrate is minus. I also do not bring subscripts with when I predict products unless it's part of the polyatomic ion. So it is not a polyatomic ion, so when I come over, I don't bring that 2 with. And then I would definitely balance this. I think you're going to need 2, because you need to have 2 nitrates and 2 silver, 1 chromate, and 2 potassiums. Last type of reaction, combustion reactions. Remember, you're going to have a hydrocarbon. Sometimes there's oxygen, not always, and then it will react with, remember, these are constant. You'll always have oxygen, and then on the product side, you're going to have carbon dioxide and water. So when you do a combustion reaction, they're easier because you don't have to worry about balancing charge. So you're just automatically going to put the CO2 and water on the, on the product side. Remember with combustion, sometimes they're a little challenging to balance, not always, but remember how we like to go in the order of carbon, hydrogen, oxygen. So if I was balancing this, I would put a 5 here. And then that would give me 5 carbons. Now I'm going to do my hydrogen. I'm going to need a 5 here so that I get 10. And then I can count my oxygens, and I have 10 here, plus another 5, and I have 15. So you remember when we have an odd number, that's where we can use the fraction 15 halves. Because 15 times 2 is 30, divided by 2 would give me 15 total oxygen. Just O's, not O2's. You can also think of it temporarily, but don't leave it like that, as 7.5. And then if you don't like it, and especially if you're using the 7.5, you want to get rid of that, then what you do is just multiply all of the coefficients by 2. So this would become 2, 15, 10, and 10. And remember, none of these are, we can't reduce that. So that's a perfectly fine balanced chemical equation. I hope that helps you predict products of the 5 types of chemical reactions.